Looking at a situation very similar to the preceding, we just make one change. The drag is proportional to v squared, which is more appropriate to slightly higher velocities than drag being proportional to v, also to different object shapes and so forth. And we're not going to worry about the details, the physical details of that. This is simply a very common differential equation which has the form mv prime equals f minus c, we'll use c for the constant, minus cv squared. Okay, this equation is then of the form v prime equals f over m minus c over m v squared. Now, this equation is not linear. We have a v squared here. Maybe it's Bernoulli, but we don't have a v term here, and maybe we could still treat it as Bernoulli with a p of t function 0, but that's probably going to lead us to some kind of a difficulty. So we're not going to attempt that, although it would be worth a try, perhaps, if we didn't have another method that's a little bit easier. And that method is simply going to be, we're going to separate this. This is just purely a function of v, so that what we have here is v prime divided by f over m minus c over m v squared equals, well, I really shouldn't have put v prime in there, equals 1. V prime is dv dt, so that this easily rearranges to dv over f over m minus c over m v squared equals dt. This side's clearly easy to integrate. This side, well, we simply have a polynomial in the denominator. If we can factor this, we can use partial fractions. Now, before we attempt to factor this, I'm going to simplify it a little bit so that it has a coefficient of 1, and we do that by factoring out f over m. We obtain dv divided by f over m times 1 minus c over f times v squared equals dt, giving us the equation dv over 1 minus c over f v squared equals f over m dt. Now, this can be simply treated as the difference of two squares. The sum and difference then of the square of square root of c over f v. Now we'll see that in a minute, and we'll continue with the solution in the very next clip.